Welcome to this problem walkthrough. Today, we'll explore problem number 926, flip string to monotone increasing. We'll break down the problem, analyze its constraints, and discuss an efficient approach to solve it. Let's dive in. In this problem, you are given a binary string S that consists only of the characters 0 and 1. A string is considered monotone increasing if all the zeros appear before any ones, meaning the sequence transitions from zeros to ones without alternating back. For example, strings like 0011 or 000 are monotone increasing because they follow this pattern, but a string like 0101 is not, as it alternates between 0 and 1. To solve the problem, you can flip any character in the string, changing a 0 to a 1 or a 1 to a 0. The goal is to determine the minimum number of flips required to transform the string into a monotone increasing sequence. The input is a binary string S of length n, where n can go up to 100,000, and the output is an integer representing the minimum number of flips needed. Let's look at the first example. The input string S is 00110. To make the string monotone increasing, we can flip the last 0 to a 1, resulting in the string 00111, which is monotone increasing because all the zeros are grouped together, followed by all the ones. In this case, only one flip is required, so the output is 1. Now consider the second example, where the input string is 010110. To make the string monotone increasing, we could flip the second one at index 2 to 0 and the last 0 at index 5 to 1, resulting in 011111. This requires 2 flips. The minimum number of flips required here is 2. In the second example, there's also an alternate way to make the string monotone increasing. Instead of flipping the second one and the last 0, we could flip the first 0 at index 0 to a 1 and the second one at index 2 to a 0, resulting in 111,110. Both approaches require 2 flips, so the minimum number of flips is still 2. Now, in the third example, the input string is 0001100. One way to make this monotone increasing is to flip the two ones at indices 4 and 5 to 0, giving us 000000000, which is monotone increasing. Alternatively, we could flip the first two zeros at indices 0 and 1 to 1, resulting in 111111000. Both methods require 2 flips, so the output is 2. This brings us to the constraints and edge cases for the problem. The string S has a length n that can range from 1 to 100,000, and it consists only of the characters 0 and 1. For edge cases, if the string is already monotone increasing, for instance, if it consists entirely of zeros or entirely of ones, then no flips are required, and the output is 0. On the other hand, if S alternates between zeros and ones, like 010101, it may require more flips compared to strings where the zeros and ones are grouped together. Lastly, because the string can be very large, up to 100,000 characters, the solution must be efficient. Ideally, the algorithm should run in O(n) time to handle the largest inputs within a reasonable time frame. To tackle the problem of flipping a binary string to make it monotone increasing, let's first consider a brute force approach. The idea is to evaluate all possible points in the string where we could partition it into 2 segments. For each partition point, we would calculate the cost of flipping characters to ensure that all characters in the left segment are 0s and all characters in the right segment are 1s. Specifically, this involves counting the 1s in the left segment that need to be flipped to 0s, and the 0s in the right segment that need to be flipped to 1s. By iterating through every possible partition point and tracking the minimum flip cost, we could solve the problem. However, this approach is computationally expensive, as it has a time complexity of O(n squared). This inefficiency arises because we repeatedly count characters for overlapping segments, making it impractical for large strings. While the implementation is straightforward, the repeated computations make it far from optimal. A more efficient strategy relies on an important observation. If we pre-compute the cumulative count of 1s to the left and 0s to the right for each position, we can quickly determine the flip cost for any partition in constant time. First, we calculate a prefix sum array, prefix_ones, I, which represents the number of 1s from the start of the string up to index I. Then, instead of explicitly calculating a suffix array for 0s, we compute it dynamically during a single backward pass. For any partition point I, the flip cost can be determined as the sum of prefix_ones, I1, and suffix_zeros, I. By pre-computing these values, we eliminate redundant calculations and reduce the time complexity to O(n), as we pass through the string only twice. Additionally, this approach is space efficient, as suffix _zeros can be computed on the fly without storing a separate array. This optimized method is significantly faster and avoids the pitfalls of the brute force approach, making it a strong candidate for solving the problem. Another possible solution leverages dynamic programming. Here, we maintain two states for each index I. dp_0 I represents the minimum flips required to make the string monotone, increasing with a 0 at position I, and dp_1 I represents the minimum flips required with a 1 at position I. Depending on whether the character at I is 0 or 1, these states transition differently. If the character is 0, no flip is needed to maintain a 0 at I, so dp_0 I equals dp_0 I1. However, to have a 1 at I, we must flip the 0 to a 1, so dp_1 I is the minimum of the previous states plus 1. Similarly, if the character is 1, no flip is needed for dp_1 I, but dp_0 I increases by 1 since the 1 must be flipped to a 0. After processing the entire string, the solution is the smaller of the two states at the final index. This approach is efficient with an O(n) time complexity, and while it can be optimized to O(1) space, managing the transitions and states adds a layer of complexity compared to the prefix sum method. The chosen solution for this problem is the optimized prefix sum approach, as it strikes the right balance between simplicity and efficiency. With a linear time complexity of O(n), it is well suited for handling large inputs. Unlike the dynamic programming approach, which requires managing multiple state transitions, the prefix sum method is more straightforward to implement, relying only on cumulative counts of 1s and 0s. This simplicity reduces the mental overhead during implementation while still guaranteeing optimal performance. Additionally, the space usage of this approach is minimal, particularly if we compute suffix _zeros dynamically, which reduces space complexity to O(1). While the dynamic programming method is equally efficient in terms of time complexity, its added complexity makes it less appealing. The brute force approach, on the other hand, is impractical for large inputs due to its O(n)² time complexity. Overall, the prefix sum approach is the preferred solution, offering a clean and efficient way to solve the problem with minimal trade-offs. In this problem, we are tasked with finding the minimum cost to partition a binary string into two segments such that all characters in the left segment are 0 and all characters in the right segment are 1. The cost for flipping a single character is 1. The first step in our algorithm is to define the transition points where this partition might occur. For a string of length n, there are n plus 1 possible transition points, before the first character, between each pair of characters, and after the last character. At each transition point, we imagine splitting the string, flipping characters as needed to satisfy the condition of all zeros on the left and all ones on the right. For instance, in the string 0101, the transition points can be visualized as splitting before index 0, between indices 0 and 1, and so on, up to splitting after the last character. These transition points allow us to systematically evaluate the cost of flipping to achieve the desired partition configuration at each possible division of the string. To efficiently calculate the cost of flipping at each transition point, we use prefix sums. These help us determine the number of zeros and ones in any segment of the string in constant time. Specifically, we define two prefix arrays, prefix _zeros and prefix _ones. The prefix _zeros array stores the cumulative count of zeros up to each index, while the prefix _ones array does the same for ones. Both arrays can be computed in a single pass through the string. For example, in the string 0101, the prefix _zeros array is 0, 1, 1, 2, 2, and the prefix _ones array is 0, 0, 1, 1, 2. These arrays allow us to quickly determine how many zeros or ones are in any segment, which is critical for calculating the flipping cost at each transition point. By pre-computing these values, we lay the groundwork for an efficient solution. With the prefix sums in place, we can now calculate the flipping cost at each transition point. For a given transition point k, the string is divided into a left segment, S0k, which should contain only zeros, and a right segment, skn, which should contain only ones. The cost to make the left segment all zeros is simply the number of ones in that segment, given by prefix _ones, k. Similarly, the cost to make the right segment all ones is the number of zeros in that segment, which can be determined using the formula prefix underscore zeros, n, prefix underscore zeros, k. The total flipping cost for transition point k is the sum of these two costs, prefix underscore ones, k, plus prefix underscore zeros, n, minus prefix underscore zeros, k. By calculating this total cost for each transition point, we can determine the minimum cost required to achieve the desired partition of the string. To find the minimum flipping cost, we iterate over all possible transition points and calculate the cost using the formula discussed earlier. We keep track of the smallest cost encountered during this process. This approach leverages the efficiency of prefix sums, reducing the time complexity of calculating the flipping cost at each transition point to O(1). Since there are n plus 1 transition points, the overall time complexity of the algorithm is O(n). Additionally, the space complexity is O(n) due to the prefix arrays. Some key insights include the importance of evaluating all transition points to guarantee the optimal solution and the efficiency gained by pre-computing prefix sums. Edge cases to consider include strings that are already entirely zeros or ones, where the minimum cost is 0, and an empty string, which also requires 0 flips. To solidify our understanding, let's walk through an example with the input string 0101. The prefix arrays are prefix underscore zeros equals 0, 1, 1, 2, 2, and prefix underscore ones equals 0, 0, 1, 1, 2. Calculating the flipping costs at each transition point, we get the following results: at k equals 0, the cost is 2, at k equals 1, the cost is 1, at k equals 2, the cost is 2, at k equals 3, the cost is 1, and at k equals 4, the cost is 2. The minimum cost among these is 1, which is the output. This example demonstrates how the algorithm efficiently evaluates all possible partitions and uses the prefix sums to compute the costs in constant time for each transition. By the end, we have the minimum cost required to make the string monotone increasing. This Python solution to LeetCode problem number 926, flip string to monotone increasing, calculates the minimum number of flips required to make a binary string monotone increasing. The approach uses prefix and suffix arrays to efficiently compute the solution. First, we calculate prefix underscore ones, or prefix underscore ones, I, contains the number of ones in the string from the start up to index I1. This allows us to quickly determine how many ones need to be flipped before a certain partition point. Next, we compute suffix underscore zeros, or suffix underscore zeros, I, contains the number of zeros in the string from index I to the end. This helps determine how many zeros need to be flipped after a partition point. The key idea is to iterate through all possible partition points, from 0 to n, in the binary string. At each partition point, the cost of flips is the sum of prefix underscore ones, I, flipping all ones before the partition, and suffix underscore zeros, I, flipping all zeros after the partition. We track the minimum cost across all possible partition points to find the optimal solution. This approach is efficient, with a time complexity of O(n), since we traverse the string a few times to calculate prefix and suffix arrays, and another O(n) loop to compute the minimum flips. The space complexity is O(n), due to the additional arrays used for prefix and suffix sums. Overall, this solution is optimized for both clarity and performance, addressing all edge cases such as strings consisting entirely of zeros or ones, and empty strings, if applicable. This is the Java implementation of LeetCode problem number 926, flip string to monotone increasing. The logic mirrors the provided Python implementation but uses Java-specific constructs such as arrays for prefix and suffix calculations. Key differences include explicit type declarations and the use of charat for string character access. The solution calculates prefix sums of ones and suffix sums of zeros, then minimizes the flips required at each partition point to ensure the string becomes monotone increasing. To solve the problem, we start by initializing the necessary variables. The input string is given as 00110, and its length is 5. We then define two arrays, a prefix array, prefix underscore ones, which will store the cumulative count of ones from the beginning of the string up to each position, and a suffix array, suffix underscore zeros, which will store the cumulative count of zeros from the end of the string backward to each position. Initially, both arrays are filled with zeros and have an extra space at the beginning and end, respectively, to simplify calculations. Next, we compute the prefix underscore ones array by iterating through the string. At each step, we check whether the current character is a 1. If it is, we add 1 to the previous value in the array, otherwise, we carry forward the previous value. This gives us a cumulative count of 1s for each position. After iterating through the string, the final prefix _1's array becomes 0, 0, 0, 1, 2, 2. Now we calculate the suffix _0's array, which captures the cumulative count of zeros as we move backward through the string. Starting from the last character, we check whether the current character is a 0. If it is, we add 1 to the value at the next position in the array, otherwise, we simply carry forward the next value. This allows us to build the count of zeros from the right-hand side of the string back to each position. After completing this backward iteration, the final suffix _0's array becomes 3, 2, 1, 1, 1, 0. Together, the prefix _1's and suffix _0's arrays provide the cumulative counts we need to evaluate the optimal point to partition the string. The last step is to calculate the minimum number of flips needed to make the string monotone increasing. For each potential partition point I, we consider the sum of prefix _1's, I, and suffix _0's, I. This represents the total flips required to make all characters before I into zeros and all characters from I onward into 1s. We evaluate this sum for each partition point and track the minimum value. For this example, the calculations are as follows. At I equals 0, the flips required are 3, at I equals 1, 2 flips are needed, at I equals 2, the flips drop to 1, at I equals 3, it increases to 2, at I equals 4, it becomes 3 again, and at I equals 5, it's 2. The minimum value among these is 1, so the minimum flips required to make the string monotone increasing is 1. Thus, our final output is 1. In this implementation of the min_flips mono-increased method, the time complexity arises from 3 key steps. The first step is the prefix sum calculation. Here, we iterate through the string s to compute a running total of 1s for each index and store it in the prefix _1's array. This requires a single pass through the string, making it an O(n) operation. The second step is the suffix sum calculation, where we iterate backward through the string to determine the cumulative count of zeros at each index, storing these values in the suffix _0's array. Again, this involves a single pass, contributing another O(n) to the time complexity. Finally, we calculate the minimum number of flips required for every possible partition point in the string. At each index, we combine the values from the prefix _1's and suffix _0's arrays and update the minimum flips. Since this step also involves iterating through the string once, it adds another O(n). Thus, each of these 3 steps contributes O(n), leading to a total time complexity of O(n). When we combine the time complexities from each step, we get O(n) plus O(n) plus O(n), which simplifies to O(n). This linear time complexity ensures that the algorithm is efficient even for larger input sizes. Now, turning to space complexity, the primary contributors are the prefix _1's and suffix _0's arrays. Each of these arrays has a size of n plus 1, where n is the length of the string, resulting in a total memory usage of O(n) for the arrays. Additionally, the algorithm uses a few scalar variables, such as n, min_flips, and loop counters, but their memory usage is constant and does not depend on the input size. Therefore, the overall space complexity is also O(n), dominated by the size of the auxiliary arrays. To better understand the efficiency of this optimized approach, let's compare it to the brute force method. In the naive approach, we would evaluate every possible partition in the string to determine the flips needed to make the left part all zeros and the right part all 1s. For each partition, counting the 1s on the left and zeros on the right requires O(n) operations, and since there are n possible partitions, the total time complexity becomes O(n squared). In contrast, the optimized approach leverages pre-computed prefix and suffix sums, which eliminates redundant calculations. By reusing these results, the algorithm reduces the time complexity to O(n), making it significantly faster than the brute force method. Analyzing the algorithm further, we see that the time complexity remains consistent across all possible input cases. In the best case, where the string consists entirely of zeros or 1s, the algorithm still computes the prefix and suffix sums for the entire string, resulting in a time complexity of O(n). Similarly, in the average case, the operations performed remain the same regardless of the input distribution, maintaining a complexity of O(n). Even in the worst case, where the string is a mixture of zeros and ones, the algorithm processes the entire string to compute prefix and suffix sums, and the complexity remains O(n). This consistency is supported by the fact that each of the three main steps involves a single pass through the input, ensuring the operations grow linearly with the size of the string. Therefore, the overall time complexity is O(n), and the space complexity is also O(n), due to the use of auxiliary arrays. To summarize, the optimized solution for the problem is highly efficient, with a time complexity of O(n) and a space complexity of O(n). This is a significant improvement over the brute force approach, which has a time complexity of O(n²). By utilizing prefix and suffix sums, the algorithm avoids redundant calculations and ensures that it processes the input in linear time. This makes it a scalable and practical solution for handling large strings while maintaining optimal performance. When solving this problem, there are some common mistakes to watch out for. First, not accounting for edge cases can lead to issues. For example, if the input string is empty, or it contains only 0s or only 1s, certain solutions might crash or produce incorrect results. This happens because these edge cases violate assumptions the algorithm may rely on. To avoid this, it's crucial to handle these scenarios explicitly in your code and test thoroughly. Another common mistake is miscalculating the transition point. For instance, you might misalign the partition index while iterating through the string, which can lead to off-by-one errors. Since partitioning logic is critical in problems like this, even a small mistake in identifying the transition point can result in flipping the wrong characters or skipping valid solutions. The fix here is to carefully verify how you're splitting the string and ensure your indices are consistent and accurate. Now, let's talk about other mistakes that can arise. Inefficient iterative approaches are one such pitfall. For example, if you recompute the flipping cost for each partition point from scratch, you are essentially introducing redundant calculations, which increases the time complexity. This is especially problematic for large inputs. A better strategy is to use prefix sums or cumulative counts to optimize these calculations. Another issue arises when the input constraints are misunderstood. For instance, you might assume the string always contains both 0s and 1s, but the constraints might allow the string to consist of just one type of character. Misunderstanding this can lead to inefficiencies or incorrect results. To avoid this, always carefully read and adapt your solution to handle all valid inputs. Finally, overcomplicating the solution can also be problematic. Using nested loops or recursive backtracking when a simpler approach like linear iteration or dynamic programming suffices can make your code harder to debug, less efficient, and more prone to errors. Aim for simplicity and focus on identifying patterns and leveraging efficient data structures to keep your solution clean and effective. To excel in interviews, there are a few key insights you should keep in mind. First, recognize that this problem is a variation of partitioning or flipping problems commonly seen with binary strings. Understanding that prefix sums or cumulative counts can be used to calculate flipping costs efficiently is a critical insight. While discussing your approach, briefly explain the brute force solution to demonstrate your thought process, but make sure to emphasize transitioning to optimized solutions like prefix sums or sliding windows to reduce complexity. Another important point is to communicate how you handle edge cases proactively. Interviewers value thoroughness and attention to detail, so explicitly addressing these scenarios can set you apart. Additionally, highlight the time complexity trade-offs between naive approaches, like O(n²) solutions, and optimized O(n) techniques using prefix sums. This demonstrates your understanding of algorithmic efficiency and your ability to make informed decisions. Finally, you might find it helpful to relate this problem to similar ones, such as LeetCode 1014, 1248, or 376, as they share techniques like prefix sum optimization or analyzing transitions between values. There are several approaches you can use to solve this problem, each with its own trade-offs. One option is the brute force method, where you try all possible partition points and calculate the flipping costs for each. While this approach is simple to implement, it becomes impractical for large inputs due to its O(n²) time complexity. A more efficient approach involves using prefix sums. By pre-computing the number of 0s and 1s up to each index, you can calculate flipping costs in O(1) for each partition, reducing the overall complexity to O(n). Although slightly more complex to implement, this method is highly efficient. Another option is dynamic programming, where you use a DP array to track the minimum cost to make the string monotone, increasing up to each index. This works well for problems with additional constraints but may require extra space. Finally, there's the greedy approach, which involves making decisions locally to minimize flips without pre-computations. While it's faster and uses less space, it may fail in scenarios that require a global optimization strategy. Carefully consider the trade-offs of each approach to select the one best suited for the problem's constraints and size. Great job! In this walkthrough, we tackled the problem of flipping a binary string to make it monotone increasing. We reviewed an inefficient brute force approach and highlighted optimized strategies using prefix sums. Remember to practice similar problems to solidify your understanding. Thanks for joining, and don't forget to like and subscribe for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!